I don't know if this is on, but I guess you can hear me, so we're good. So yeah, I'm Francesc Campoy, and that's not on the slide, so I don't know what I point there. But today I'm going to be talking about machine learning on source code. There's a little bit of an introduction of why is this even a thing. So I'm sure you've all heard this phrase, software is in the world. And this has been going on for a while, but it keeps on accelerating. And I didn't realize how much source code there's in the world until I actually started trying to figure out how much source code is there outside, right? Like in open source, but also not even open source. How much source code do we have in the world? And I started by looking like prehistory, or at least pre-RGB. And you look at Adobe Photoshop. This was a pretty powerful tool, even though there were no colors. And this was 128,000 lines of code. And for me, as a programmer, this seems like a lot. But also as a user, you know, it's not that much. Windows 3.1 in '93, 4 to 5 million lines of code. And this was pretty serious. I used to play Prince of Persia on this. So, you know, that works. OpenOffice, 9 million lines of code. Chrome, 18 million lines of code. You all recognize? Windows XP, I was going to say Vista. Windows XP, 45 million lines of code. And this starts to be a decent amount of code, right? And this is a Ford car, pickup, huge pickup. 150 million lines of code running in the car. Yeah. So when you think about 150 million lines of code driving the car that you think you're driving, things start to get scary, right? And when you think about the fact that basically no matter how good you're writing code, there's bugs, right? Say there's one critical bug per million lines of code. You have 150 in that car, right? That's scary. And if you look at Google, 1 billion line of code. And if you ask GitHub, they will tell you they don't know. And actually, if you keep on asking more, they'll tell you that it's somewhere around like 4 to 5 billion lines of code, but they don't really know because they don't count it, which is interesting. The problem with this is that, yeah, the code keeps on evolving, and we keep on having more and more lines of code, which is great, but we keep on using the same tooling, right? Yes, we have better editors. Sure, but those editors, other than auto-completion, they don't do much. And especially editing the code is just one of the pieces, right? We have great tooling now for once you want to test things, continuous integration, continuous deployment. All of these things have helped a lot the industry. But the editing part of things, well, yeah, there's Vim and Emacs and VS Code and all of these things, but it doesn't really has changed that much. And if you think about the way, not the way we write code, but the way we review code, it's even worse. How do we review code? Well, you read it. Good luck, right? There should be better ways to do this. And we believe it can be machine learning. With all tools, you can do cute stuff with cute dogs inside. And they will probably survive. Unless it's me building the house. I'm really bad at that. But if you try to build something as big as Google, you're going to need better tooling, right? And that's where what we're trying to do is apply machine learning to the previous tooling we had to build better products. So now, yes, I am Francesc Campoy, and I'm going to be talking about machine learning on source code. I originally created this talk for GopherCon, and it was a much shorter version. And people thought it was machine learning in Go, and it was actually machine learning on Go. So we're not going to be talking about how to write machine learning, but actually how to use machine learning to write code. So I'm VP of Product and Developer Relations at Sourced, which is a tiny startup. We are now 35 people, and we work on this. This is what we do, machine learning on source code. Machine learning for large-scale code analysis. And I'll show you a little bit what we do. But this is really not a product pitch. This is about like what we're trying to do and like the ideas and projects that are around. I'm Francesc on Twitter, and if you want to use hashtags, ScaleSF is apparently the one for the conference, and MLonCode is the one we use. So we're going to be talking about what machine learning on source code is. Then we're going to talk a little bit about the research and where it's going. Then we're going to be talking about the way this actually works for us, right? Like, what can you do? There's machine learning is super cool. There's a lot of really advanced techniques. But what does that mean for us? And then we're going to be talking about, OK, in the future, assuming that everything goes well, what could we do? What will the world look like for developers in 20 years? So what is machine learning on source code? Simple. It's machine learning that you apply on source code. That's it, right? Machine learning on source code is simply the fact that instead of having the input data being, say, images or text or videos or anything like that, you get source code. That's it. If you're doing that, that's machine learning on source code. I do not care exactly about what it is. If you're fancy, you might call it AI on source code. I don't care. We call it MLonCode, and it's any ML technique applied to source code. So what are the fields that are related to this? Data mining is one of them. Why? Well, when you have billions of lines of code that you want to analyze, that's a lot of text. That's a lot of data, right? You want to analyze it correctly. There's a lot of things that you can learn from data mining. Text, human text, and programming languages are different. But they're not that different. They actually share a lot of aspects, right? They have grammars, they have syntax. All of these things coexist, although they're not exactly the same. I will talk a little bit later on why there's a little bit of a difference on the way we handle natural language and programming languages. But we can learn a lot from NLP. Natural language processing, most of the techniques that they use for natural language processing can be adapted quite successfully to machine learning on source code. And then graph-based machine learning, because source code is graphs. Source code, if you think about go to definition, that's a relationship that is over a tree, and all of a sudden, there you go. Now you have a graph, right? So we need to do graph and machine learning on top of those graphs all the time, which is really interesting and actually quite hard. I'm VP of Product and Developer Relations, so I don't do those things. That's the VP of Machine Learning that does all of this cool stuff. But I know enough to know it's really hard. So yeah, what do we need for this? Lots of data. Luckily, we have it, right? We need to fetch it, but that data exists. There's lots of data, really, really lots of data. You need some fancy ML algorithms, and then luck. Hopefully, everything works. Not always. When you do machine learning, there's a lot of different aspects that can change a little bit the way a model is gonna act. So there's a lot of trial and error involved in anything related to machine learning and also machine learning on source code. So first challenge, data retrieval. We have billions of lines of code out there. How do we fetch them? Git clone is not the solution. So there's a couple data sets that are very useful. One is GitHub Archive, or GH Archive. I think they cannot technically say GitHub. That's why they're called GH Archive. And that contains a lot of metadata about source code on GitHub. What we've done is we created a different one, which is public Git Archive, that does not contain only the metadata, but also all of the source code on GitHub for repositories with 50 stars or more. That's a lot of repositories. That's 50, no, let me see. Repositories, 182,000 repositories compared to previous efforts that were like one order of magnitude smaller. It's around 3 terabytes of source code. And it does not only contain the current source code, but actually all of the iterations before. You have all of the blobs in the Git repositories. In order to do this, there's actually a lot of fancy things that we do. One of them is what we call rooted repositories. GitHub has an API that allows you to know whether 2 repositories are a fork of each other. That, unfortunately, is pretty useless because most people will get cloned and then get pushed somewhere else. And the API will never know about this, right? So we actually do an analysis on the commits to figure out whether 2 projects are independent or not. And this allows us to minimize a lot, like write blobs only once, all of these things. There's much more than that, but it's the least interesting part, just fetching the data. The second part is analyzing that data. And this is where things start to get interesting, because when you think about source code, what is source code? Like, if you're going to analyze this, how do you do it? And the easiest way is to say, source code is bytes. That's it. You write with bytes, and that is the code, right? That's it. You can fetch this, you can feed this to a machine learning model, see what happens. And it actually works, which is kind of crazy. But this is like the lowest level that you can say. It's like, code is text, which is bytes. Cool. But also, you can say, actually, that's not how I read the code, right? I read package. I mean, I do Go all the time, so I'm sorry for people that do not know Go. It's pretty straightforward. Do not worry too much, and there's nothing fancy to do. So I read here package main. That is what I read. Those are tokens. Sure, so let's say you can also have tokens. So token is a different level of abstraction. And this allows you to give more information to the machine learning model that you're training. You also have abstract syntax trees. And as soon as you start adding things on top of an abstract syntax tree, what you get is a graph. You have many, many different kinds of graphs. You have control flow graphs. You have definition graphs, semantic graphs, all of these different kinds of graphs. You want to learn from those, and it's actually really interesting. This is where most of the research is, right? The first levels, you can do fun things, and they're cute, but this is where the research actually goes. So yeah, so we have sequences, trees, and graphs. So it goes from easier to understand and easier to do to actually quite complex. So all the things that you need to do when you want to analyze code. Well, first thing is you need to know what language a program is written in. That's the first step. The second one is you need to be able to parse that language. Then you need to be able to extract the pieces that you're interested in. And then you also may want to do that over time, right? So say I want to find all of the function names. Sure, when, right? Head, a month ago, what commit do you want? All of those things are also very important. And then reference resolution, which is basically you calling the function foo. Where is this defined? What is foo, right? And that could be in the same file, could be in a completely different repository. You never know. We have a bunch of different projects that we implemented for each one of them. The last one for reference resolution is called Kite, and we did not create it. It was created at Google, and instead we hired the person that created the project. That was easy. It was not easy, actually, but it worked well. So these are a bunch of different things that we've created over time. And what we've done is we put everything together in a single product. And that's what we call Source Engine. Just quick demos. So Babelfish is, that's pretty right. So Babelfish is the project that allows us to parse any language and extract tokens from it. So say you have some Java code. And here on the left side, you have the Java code. On the right side, that's an abstract syntax tree. And we call that abstract syntax tree universal. The universal is just about the fact that there's a common format for all languages. It doesn't mean that all abstract syntax trees look the same, but rather than we have a protocol buffer definition for it, right? It's pretty much it. And then there's also language agnostic tags or roles. So for instance, when you say this hello world, it's going to say that's a node that has a bunch of roles. It's an argument that is positional, and the type is string, right? That type UST string, it is something that you can query for. String. And now you're going to get only the strings, right? So you can see on the right side, those two nodes those are the strings they have. Why is this cool? Well, this is cool because, actually, let me copy this. If now I go and I use go, and we have this, and I do exactly the same query, we do exactly the same thing, and now we have the strings, right? So what we've built is actually a way to parse programming languages in a language agnostic way, which sounds weird, but it's actually really powerful. Because if I want to say, I want to use all of the variable names, I do not care whether this is Java, PHP, or Go. Variable name is pretty well defined, right? So just find those. And that's how we're doing it. This is the project. Then we've integrated that also in a SQL environment. So you can do select star from repositories. And this is actually analyzing a bunch of the repositories. There's 30 repositories here. That is all of the source code under the Kubernetes thing, the Kubernetes organization in GitHub. So, and that is SQL, which is pretty straightforward. But the cool thing is that as soon as you have SQL, you can stop using SQL and use Jupyter, which is much cooler. And you can start doing quite interesting things. I will not get into the detail of how all of this works. But you can do, let me show you. The one that is interesting is the one with colors. So here, for instance, you have this query. And this is saying, hey, I want to find all of the repositories. Over all of the repositories, I want to find all of the files that are in head. And then I want to find the language. That language function is something that we've added to MySQL. It's a custom built function. And it tells you what language it is. So with that query, after 5 seconds, you're able to tell that is not up to date at all because that is not Kubernetes. Kubernetes, this from a previous analysis that I did, but you're able to see what are the common languages that you find. You can do the same thing, but in a little bit more complicated way, using that UAST concept that we talked about before, and say, I want to extract this thing. Function group / alias / identifier. Those are the function names. I want to extract all of the function names, no matter what programming language this is written in. And then you're going to be able to generate things like this, where you have word clouds for different languages. Right? Those word clouds have been generated with a single query. We do not care what programming language this is. Why is this important? Well, this is important because the next step is going to be getting all of this data and using it to train models. In order to do machine learning, you're asking the machine learning scientist to first know how to parse code. They will never finish, right? So we have two different pieces. We have data retrieval, which do these kind of things. Then we have machine learning, which is the second part. Before I continue, are there any questions about this part so far?
What language do you use both? You said Go, Java?
Yeah, we have basically all the languages that are like well known. And as I say this, I don't know if we have Scala, which I'm very sad for this conference. But I think we do. But we do have like Java, Go, PHP, Ruby, all of those. The latest one that we had that we were missing was C, C++, because parsing C is really hard. And parsing C++ is basically impossible. We finished that recently. So those are, other than that, basically any language that you can imagine is pretty easy. We probably have it, and if not, it's pretty easy to add. That's the whole point. Every parser is actually written in any language you want, which makes it much easier, because parsing Java in Java is much easier than parsing Java in, say, PHP. Right? You can choose the language that works better for your problem, which is really good.
But I have a question here. Suppose if you do symbolic debugging, actually, or something like that, you have the trees which you draw. For simple programs, you could draw the graph pretty nicely.
Yeah.
But when the program becomes extremely complex, actually, now you have to also use concrete and symbolic kind of notions, actually, right? So how are you guys dealing with the graphs themselves? They could become humongous.
Yeah, we can talk about that a little bit later because it's kind of out of the scope, but that's exactly what Kite does. Kite is a project that was created internally at Google to create cross-references across all of their code base. The code base, Google 3, that contains 1 billion lines of code, right? So doing cross-references over that data set is really hard, and they were able to do it, and now it's open source.
It would be great if you could talk a little bit about what did you learn from this code? Like, you're talking a lot about how you do it, which is
learning from source code. That's the next.
How you learn. Okay, I want to know, what did you learn?
We're getting there.
Okay.
Yeah. Okay, so let's continue with the learning side of things. Like so far, yes, we've talked about how to fetch source code and how to analyze it. Now, the next step is learning from that source code and see what we can actually build with that. So in order to learn from source code, one of the things we're going to be doing is neural networks. And I'm not going to get into detail of what neural networks are, because it's either I do not explain much, or we spend a year here. So I'm just going to say that neural networks are a very, very useful piece of technology that allows you to basically, by the power of insisting on, no, the result should be this, finally actually convince that neural network that the result is actually that, right? I like to use it, I use the metaphor or the analog of, it's like a puppy that you need to keep on saying no, 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 and eventually it learns and it's able to do things that are useful. Here, we're going to do kind of the same. So this is the MNIST data set that I'm sure if you've done any machine learning, you've seen. Where we're getting an image, getting all of the pixels, and feeding it to a neural network. We don't really care about the structure, the architecture, and that's going to tell us, this looks like an 8, and that's how it comes up. It's around 0, around 1, not exactly 0, not exactly 1, because there's the prediction. And this is actually something we're going to use in a minute. The whole point of neural networks, and I'm not going to get too much into details, is the fact that we want to learn things that are actually not necessarily doable with algorithms. Why is this? If you want to do language analysis, very often you need the full source code, right? You need not only the source code that you're analyzing, but also all the possible dependencies. That is actually really hard to achieve. It is very, very complicated to do it over open source. And especially depending on the build system, every single programming language might do this differently, right? So that is really, really hard. What we're trying to do is, using machine learning, be able to do some predictions that are based on partial information. That's why we're doing machine learning rather than traditional language analysis. So one thing that you could do is say, well, I'm going to give you 10 tokens, you predict the next one, right? So if you see for I colon equals 0, I is less than 10, after the I is probably a plus plus. It doesn't mean that it's necessarily a plus plus, but probably, right? Because if it was a minus minus, that'd be pretty weird. You would be counting down while comparing to something that is up. So these things, a neural network is able to predict quite well. What if you don't want to say 10 tokens, but actually you want to do something over sequences? We talked about the fact that code can be seen as a sequence of characters, a sequence of tokens. Well, in that case, you're going to start using recurrent neural networks. And these are very useful for a bunch of different domains. One of them is language translation, right? Language translation, you're going to translate a sentence, you don't know how long it is, from a language to another language, and that's going to be some other sequence. There's no the sequence that enters and the sequence that exits is not necessarily the same length, right? So it's going to be much more complicated, but recurrent neural networks is something that we use all of the time. And you can use this for code generation. And I don't know if you've seen this before. It's a typical example what people do with Shakespeare. I decided to do it with Go. So what I did is I used a recurrent neural network, and I trained it with the Go standard library. And I asked it, OK, now you know Go, write some Go. This before training, which is not exactly Go, it's not valid completely. After just one epoch, so just seeing the data set once, you start seeing things like this. And this is quite interesting because this actually looks like Go. It will not compile, it is not syntactically correct, but if you look from far away, I would say this is Go. Especially if error is not nil, return error, that's the most Go-ish line of code ever. We have Go, but still, this is not totally perfect, right? And you keep on training, and it does things that they actually look like Go. But this is not Go, right? Like this will not compile. There's things like, for instance, I mean, it does do the indentation correctly, the parentheses, the brackets. Most of it is good, but for instance, that if not OT close, that's not Go, right? So it looks good, still not perfect. If you keep on training it, eventually you get to something that is pretty decent, but never good enough. The problem is when you're generating Shakespeare, at least for me, if you generate Shakespeare that is slightly wrong, it's still Shakespeare because it's weird. That's the point, right? But if you generate Go and you generate something that is not exactly Go, then it's not Go. It doesn't compile, right? So it's a little bit different. The NLP techniques are not going to help us completely in this problem. There's other research problems that have been presented. There's a lot of research, and actually I'll give you a list of them that you can check out. There's one called var misuse. And var misuse is about this task, where what we do is we train a neural network to, given a program, we remove just one identifier from the whole source code. And then we ask the neural network to predict what identifier goes there, right? Is this useful? Actually, yeah, incredibly useful. And it's not about predicting what is the token that is missing. But actually, if you do this over every single identifier, you might be able to predict when the token that you find is actually wrong, right? Someone actually did a copy-paste error. This happens all the time. I'll show you how this works in a minute. There's another one that I really like, and it's much more complicated. This is about learning from graphs. And when you're learning from graphs, there's many ways of doing it. One of them is to, rather than having a graph, representing a graph and feeding it to a neural network is actually really complicated. So you need to find different alternative representations. One of them is finding all of the paths across all of the nodes. So now instead of having just a graph, you have a sequence of paths, right? And then you can feed that. And then you can train a neural network with that. That is what Code2Vec does. And Code2Vec is very, very good because it uses embeddings to actually be able to predict really useful things about code and identifiers. If you want to know more about machine learning on source code, we actually have a repository with all of the research we read, all of the things we write. Everything is there. It's super interesting. I have not read the whole thing, but some of them are like good for beginners. Those are the ones that I'm reading, and they're very, very, very good. Oh. OK, so now we have neural networks. We've trained them. It's cool. We might get some decent accuracy, but it's never very, very, very high. What can we do with this? So these were, rather than trying to predict things and generate code, what we're trying to do is actually reverse the problem and say, can we use our predictions to tell whether something is expected, right? So in the previous problem, we were saying things like, we're missing like for I equals 0, I is less than 10, what's going next? Sure, we're going to predict something like saying, actually, this is probably a plus plus. We have a 99% chances of this. Sure. OK, the thing is that if we see a minus minus, we're going to be able to see that the prediction for that, which is also something that compute every single time, is going to be incredibly low. So now you're going to start using that information, which is somehow like the amount of entropy, like the amount of information that a given token is bringing to the program. You're going to be able to see the prediction is so low that probably there's a problem. And we can use that. We've used this as an attention model for code reviews. You're reviewing some code. Say you're reviewing this decently large change. And you're reading all of this. How do you review this? Well, the way you're supposed to do this is line by line, reading every single thing, and paying attention, full attention to every single line of code. Imagine if instead of doing this, we're actually able to find which pieces of the code are the least expected. And least expected doesn't mean they're wrong, but they're actually more complicated. There's more information in that piece of code than in the rest. The rest may be public static void main, right? Who cares about public static void main? You don't review that. You review the pieces that are interesting. So imagine if you could do something like this. And this is something we've built, and it works pretty decently. I applied it to this problem. And here, very, very quick, it said that minus minus has a super low probability of actually being correct. It should be I++, right? Those are things that probably in a big code review are things that you might miss. So what we're doing is trying to help code reviewers and authors write better code through tools that are going to help them. They're not going to replace them, but they're going to help them do a better job. For var misuse, this is a typical problem. This is how you open a file in Go, and you do defer to make sure it's closed at the end. And I'm lazy, so I do copy paste, right? And now I write this program. I'm opening A, opening B, and then copying from A to B. And this code is wrong. Why? Because actually we're closing from twice, right? And this is where the var misuse is going to actually tell you, hey, like maybe this is OK, but there's a very, very low chance for this. We're predicting with a very high accuracy that this should actually be to instead of from, right? And we can actually provide that as even a suggestion on GitHub reviews, which is really cool. So the author can be like, oh, yeah, true, and just click and fixed, right? These kind of things is some of the things we're working on. Code to vec, I'm actually going to show in a minute, because I have a very cool demo for code to vec. There's one more thing that we have is using deep learning to understand how identifiers should be split. And we wrote a blog post about this. We're using bidirectional, long, short-term memory recurrent neural networks, which is a super long way to say it's a very complicated thing. And at the end, what we're able to do is, given some code, given a sequence of characters that did not have underscores or no camel case, no snake case, none of those, we're able to predict how we should split this. And then we're able to use that to predict whether something has been capitalized correctly, for instance, or whether the hyphens are actually the hyphens. The underscores are put correctly. So a couple demos. The Learning Go, I left it here. So Learning Go, I will publish these slides, but this, I started running it on Colab before the talk started. And you can see how after not very long, it does generate a lot of output though. So this is training. Let's see. OK. Let's see. So yeah, this is the input sentences and the output that it's generating. It's still pretty bad, but if I'm able to find predicted output, this is a big. Oh, there you go. So this, after 30 minutes, the code is generating. And this starts to look pretty good. It's using a TPU, which, by the way, it's free, and you should definitely check it out. I don't work for Google anymore, but still really cool, because it's free. So Colab is super cool for this. Demo's very, very nice. But yeah, this film for like 30 minutes, whatever the time has taken for the talk, right? So it's pretty impressive. Code to Vec. This one is something that we have not built. This is from the Technion University in Tel Aviv. And they parse it, they parse the program, they show those paths with which paths are the most important ones are shown as being thicker. So basically the neural network is actually trained to learn which paths are the most relevant and then use those to predict the name of a function. So in here, this function is called f, but it's saying with a 99% of accuracy, not accuracy, of certainty, that this should be called sort, or bubble sort, or things like this. I'll let you check it out. I think it's very cool. Embeddings also allows you to do things over embeddings of identifiers. So what is count similar to? Well, count is similar to size and index and sum and max. All of those functions tend to look very similar. Or equals and to lower. Equals ignore case, right? So you can actually do those mathematics inside of this really large, very high dimensional space where you can start doing these things and computing whether a function name is valid or not, whether it actually represents what the code is doing. And the analogy is the typical one. Receive is to download, as send is to upload. You can play with those and change them. This is actually pretty cool. You will see that this works really well for the examples that are here. As soon as you start changing the code, things start to work not as well. But this is research, right? What we're trying to do is make this research into things that you can actually use. And the neural splitter, I don't have time to do it. So actually, let's go through this really quick. So this is the train model. I am very satisfied, thank you. So this is the neural model. We're loading it. This has been trained over public Git archive, which is 3 terabytes of source code. So it wouldn't take longer than this. And then you get the things like, yeah, like I think this is a variable. You just write like that, and it's going to actually figure out how to separate it. And writing some extra Python, you can actually do it. So it will convert that. So I think my time is over. That's how you're supposed to write it in Go, right? Like this is pretty straightforward, but still very useful. So what does this look like when we're using it? What we're building is an assisted code review, right? This is what we're building now. This is our first MLonCode product. And the way this looks right now, this is live on GitHub, is something like this. You have, oh, I lost the comment. Let me refresh. Yeah, so you have lookout staging, that's a bot. And the bot is saying, hey, like these lines of code here are actually very similar to 118 to 163. And if you look at those lines of code, you will see that they look very similar, but they're not exactly the same. We're actually doing code clone detection over code that has changed slightly. So if you have two different functions and you change some variables and you change things like this, we're still able to detect that you should probably be just writing this once and not repeating your source code over and over. And it does many other kind of analysis. So what are the things that we're working on? We're working on automated style guide enforcing. So learning the style of your source code from your source code and then applying it to your no PRs. So the whole idea behind that is the fact that we do not want people to spend their time saying you need to have 2 spaces after the double bar to have a comment, right? Like a machine can do this much better. And you may write tools for this. There's many linters that do this very well, but you need to write it for every language. If we were able to actually learn it from the language that is already there without having to write the tool, would be much better. We also want to do back prediction, and then one day maybe automated code review, not assisted, but actually automated. How far can we go there? I think there's a lot of the different things that we can automate. And then code generation by having conversations with the computer, which is kind of like a compiler, but the compiler will be asking you questions about, hey, you want to sort this? Do you want to use the normal algorithm? Do you want to use something else? And just to make a lot of assumptions and try to minimize how much interaction you need to have with the compiler to write a program. And I think that'd be super interesting. So will developers be replaced? Are we trying to replace developers? If you know any architect, I don't think that architects would say that CAD killed their profession, rather the opposite, and that's what we're trying to do, right? Like what we're trying to do is write better tools, create better tools, so developers can be empowered to do better things. And we're hiring. Yes, we're hiring. If I don't say this, we're hiring like product managers and like engineers and everything, really. We're only 35 people, so we're definitely hiring. So if you're interested, find me around, and I do have stickers. Thank you.
Thank you. That was absolutely fascinating. I mean,
Thank you.
I do NLP, and so doing it on code is a great idea. I think we have time for like one question, and then we need to move on to our final talk of the day. Anybody want to volunteer here?
If not, you can also ask questions
You can always find
to my email, francesc@source.tech, or @francesc on Twitter.
All right.
Thank you.
Thank you again.
Thank you.